All right. Good morning, everybody. Everybody, all three of you. Good to have you here. So this is our last review. I did get one request that I'd like to share with everybody. Somebody said, could you just quickly go over the first and the second derivative tests? So here's a quick slide on this. So what does the first derivative tell you? It tells you instantaneous slope. By the way, that's what that's supposed to read there, written kind of quickly. Instantaneous slope. And when it's positive, it's telling you the graph is going uphill, it's increasing. And when that first derivative is negative, it's telling you the graph is decreasing. And when it's zero, it means we're at this little horizontal resting point, either a max or a min. So whenever a problem asks you, give me the intervals on which the function is increasing and decreasing, then the first derivative is going to be the thing you're going to want to use. Okay? On the other hand, the second derivative tells you concavity. And so what you're trying to do at this point is, I mean, yeah, I got to turn off. We got people coming in here. All right. We got that taken care of. So anyway, the second derivative test is used whenever you're asked for intervals of concavity. So when you find the second derivative, you are told whether it's the sign tells you whether it's concave up or concave down. A positive sign, concave up. A negative sign, concave down. A zero tells you we have a point of inflection. And so if you're asked to find out anything about the concavity of a graph, that's when you use the second derivative test. Okay, let's see, I got a message here. No, all right, we don't. So anyway, I said I would relay that, and there's the answer to that question. So it's always hard for me to remember what I've done in each section. So I'll show you some of the, I don't know. Why don't you just, I guess let's just open it wide up. What kind of a problem or what kind of a question might you have as we do this final preparation? Welcome to those that came in after we started. Marissa, Jordan, Claire, glad to have you here. I do have a message. Could we go through 59 and 60 in the review? And I just got a 27 request. All right, 27, 59, 60 are the three that I have received. All right. Well, let's take a look at 27 first. Let's see, do we have? We did number 28, so let's go, we'll go nearby there, I guess. Let's do 27 over here. Number 27. Okay, number 27. Second page. No, I'm in the wrong place. Okay, let's see. Table of contents. Here you go. Chapter 4 and review exercises. All right. Now we're in the right place. All right, number 27. Let's grab that. Whoa. That's not what I wanted to do. That's interesting, huh? All right, let's try that again. Copy image. All right, here we go. And what are the directions back there? Identify the open intervals in which the function is increasing or decreasing. So this is going to be the first derivative test, right? All right. So let's go back, number 27. So let's find the derivative. So where are we here? We got a. All right. Just like you, I've got to review. What do we do when we have a constant to a power? A constant to a power. Where is that? All of a sudden I can't, oh, there we go. Yeah. So it's the natural log of 2 itself times the natural log of 2. Okay, so we take the derivative of 2 minus t, which is the derivative of 2. Let me change this so we get the black. So the derivative of 2 is 0, and the derivative of negative t is negative 1. So you know what? Let me start this out. So we have a product rule here. We have two things to take the derivative of. This times this. Okay, the first of the second. And now for the derivative of the second, we have to take what? The natural log of 2 times whatever it was before, 2 to the t. Okay, plus the second times the derivative of the first, which is like we did a few seconds ago, negative 1. Okay, so we got all kinds of things going on here, but we can factor a 2 to the t out. And what's left is natural log of 2 times 2 minus t plus negative 1. Okay, now the big issue here is, when is this equal to 0? Well, when will 2 to the t ever be 0? It can't, right? Nothing you put on 2 will ever make it a 0. You can have really large negative number that'll make it really close to 0, but it won't ever equal it. Okay, so we go to the second part, natural log of 2 times 2 minus t plus a negative 1. So let's add 1 to both sides. I don't know. Let's see if we want to do that. Well, let's try that. Let's leave it at a 0 and let's see what goes on here. Okay, let's multiply this out. So natural log of 2, so that would be 2 times the natural log of 2 minus t times the natural log of 2 minus 1. Okay, so if we add 1 to both sides, natural log of 2, so this is just a constant here, whatever that is, minus t times the natural log of 2. So this we could, here, let's just do that on our calculator. Natural log of 2. Let's see, got that down here. Let's pull up the calculator. Okay. Where is natural log on here? There it is. So 2 natural log times 2. So we can subtract that from both sides. So if you subtract 1.39 from both sides, you're going to get negative 0.39 on the left. Equals negative t times the natural log of 2. That's supposed to, I don't know what I was doing there. That's supposed to be a natural log. And then we could divide both sides by negative natural logs. So we get t equals negative 0.39 over the natural log of 2. And the natural log of 2 is again what? 2 natural log, negative 0.69. P equals a positive, what? It's about 1/2. Let's do that real quick. 0.39 divided by 0.69. So T equals 0.57. So that's when the derivative equals 0. So now we've got the dividing line. So now you kind of set up your fence posts. I'm running out of space, so I'm going to have to go to the right here. So you set up. You've got your critical value of 0.57. So now you got to take a number less than 0.57 and a number greater than. And we want to know the derivative. So see, move that over a little too far. Let's get this out of there. Okay. So where's our derivative? Our derivative is, yes, we don't have the simplest statement. Yeah, I guess our derivative is right here. We can use this line right here. Okay, so let's take a number less than 0.57. How about 0? Okay. So 2 times the natural log of 2. This is going to wipe out. So we basically have 2 times the natural log of 2 minus 1. Let's figure that out real quickly. 2 natural log of 2 times 2 minus 1. And you can see it's going to be positive because it comes out to 0.38. So positive, so increasing. And then over here, let's take a 1. Okay. 2 times the natural log of 2 minus the natural log of 2. Well, 2 times the natural log of 2 minus 1 times the natural log of 2 is the natural log of 2 minus 1. And let's just do that real quickly. 2 natural log minus 1, and you can see we're going to have a negative. So this is negative, so decreasing. And I just want to double check back with the problem. Number 27 said identify the open intervals on which the function is increasing or decreasing. Okay, so what we got here is from negative infinity up to 0.57 increasing, and the other interval is 0.57 to infinity, appears to be decreasing. And we can take a look at Desmos to see what that looks like. Let's see, what's our function? 2 minus t parentheses times 2 to the 2. Okay, Desmos. Okay, 2 minus x times 2x. All right, so, yep, there's that point. I said 0.57, it's actually 0.56. And before that, what did we say? It was increasing, and after it, we said it was decreasing, and that's what the graph shows. Increasing before 0.57, decreasing afterwards. So, all right, so that was number 27. Sorry, that got spread out quite a bit. Let's see, I got a message. What's that? "47 is added to the list. Thank you. Okay, the next one I have down is number 59. So let's take a look at 59. Let's find some, let's do that over here. Okay, number 59. All right, 59. Here we go. Okay, it's a limit. So what's the limit? As x approaches negative infinity, what's going to happen to this? Well, you notice the numerator is going to win because it has a higher power to the second power as opposed to the bottom. So this is going to go to some kind of infinity. So let's just check what happens on the top. When you take a negative large number and square it, the top's going to turn out to be positive. On the bottom, when you take a negative large number, it's going to be negative, and a positive divided by a negative is a negative. Therefore, just based on that analysis, it's going to approach a negative infinity. I don't know. Whoever asked that question, so one more time. Because the top wins, you know it's going to be infinity for a limit. And then the other part you got to check is the sign. Because a negative infinity squared will be a positive infinity. The top will be positive, the bottom will be a negative, a positive divided by a negative. It's going to be a negative infinity. That's number 59. Number 60. Another one of those limits. All right, got to get my bearings here. Number 60. Copy. Number 60. Okay, back. Okay, let's do number 60. So, on the top. So, first of all, we have a second degree on the top, but because it's, what, the square root, that's really going to be reduced to a first power on the top. And on the bottom, we have a first power. And when the powers are tied, what do? We do the coefficients. So, the coefficient on top, what's the coefficient of the x squared term? It's a 1. And what's the coefficient on the bottom? It's a 2. So it's going to be 1/2. Now, we got to check the sign. We're approaching negative infinity. So when you square a negative infinity, it's going to be a positive. And then when you take the square root, it's going to be a positive. On the bottom, when x approaches a negative infinity, it's going to be a -2 times the negative infinity, which is a positive. So they're both positive. So it's approaching positive. Let's go through that one more time. So the degree on the top, because it's a square root of x squared, that's going to be a degree 1. As we approach infinity, so the powers are basically tied, top and bottom. That means it approaches the coefficients of those two terms. The coefficient of the x squared square root is going to be 1. And on the bottom, we have a 2. So it's 1/2. Oh, 1/2. What am I doing? My apologies. I forgot what I said. So it's going to be a 1/2. But now what about the sign? On the top, it's going to be a positive. On the bottom, it's also, yeah, so there's your limit, 1/2. Number 47 has been requested. Let's take a look at number 47. And what are the directions here? I got to look. Find all relative extrema. Use the second derivative test if you need it or where applicable. All right. Find all the relative extrema. Okay, now let's go back. Number 47. Okay. Let's try that one more time. Okay, I'm having trouble getting this. My apologies. Copy. Okay, here we go. All right. So find all relative extrema. So we know we're going to have to do the derivative. So let's get started at that. So yeah, maybe we should rewrite the problem before we begin. So we have f of x equals 2x plus 18x to the negative 1. Derivative, 2x minus 18x to the negative 2. Okay. And we could rewrite that as 2x minus 18 over x squared. The question is, let's at least start with, if we're trying to find extrema, we're going to definitely need to set the first derivative equal to 0. Okay, so, well, we could add 18 over x squared to both sides. We could now multiply both sides by x squared. We can divide both sides by 2. And then we could take the cube root. So it looks like that's a critical point where we've got some either a high or a low. Okay.
So you missed one.
What did I miss?
The derivative of 2x is 2.
Oh, yeah. Thank you. That is correct. So, thank you for catching that. Whoop. So, 2x squared. X squared equals 9. So now we get two roots, plus and minus 3 appear to be critical values. Okay? So now the question is, are those maxes or mins? Here's where the second derivative would be handy, right? So let's go back up to the top and let's take the second derivative. So here's our first derivative. Let's rewrite that. 2 minus 18 x to the negative 2. Yeah, I forgot to take that x out right there. Thank you. All right, so 2 minus 18x to the negative 2. So that's our first derivative. Second derivative. Well, constant, nothing. Power rule, negative 18 times negative 2 is positive 36. Reduce the power by 1. So we get 36 over x cubed. And that's our second derivative. So now all we got to do is take these two and plug them in. So what happens when you plug in a positive 3? A positive 3, when you cube it, is 27. And 36 over 27 is positive. Therefore, what did that was it. So I have plus 3. It's concave up. And that means this must be a min. At negative 3, negative 3 cubed is negative 27. When you divide, you get a negative. So that's concave down. So that means that must be a max. Okay, now the only thing we haven't done, did we get an interval there? Anybody remember? Number 47, where we given an interval? Doesn't look like it there. How about on the directions? No, there was no interval. So we don't have to really check endpoints. Okay, let's just check, see what the graph looks like as a kind of a double check. So basically I got the max at negative 3 and the min at positive 3. So decimal, what do we got here? Function is 2x plus 18 over x. Okay. 2x plus 18 over x. So you can see so at negative 3, you can see how we've reached a relative maximum. And at positive 3, we've reached a relative minimum. And what was the problem asking us to do? Find all relative extrema. So the only thing I really need to do is to write relative, min, relative, and we're done. So 27, 59, 60, 47, I think those were the requests. Now, how do you know when to apply the second derivative test? Would you just apply, well, okay, Claire, that's what I talked about in the beginning. The only time you need the second derivative test is when you want to know concavity. The other thing, it might be helped, though, to tell if it's a max or a min, like we just did here. So here, I did the first derivative test, and we found out we had a plus 3 and a minus 3, but we couldn't tell which was min or which was max. The second derivative allowed us, so it was a weapon that allowed us to see, oh, that's right. If we check concavity, if it's concave up, then it's got to be a minimum, and if it's concave down, then it has to be a max. So the second derivative is a handy tool for that. It also tells you It might be helpful to know when you have a point of inflection too. So that's, I don't know if that answers your question. So the second derivative is for determining concavity, which can tell you, hey, is that a min or a max? And it also could help you find points of the, the points of inflection. And if you don't know points of inflection, then you couldn't determine the intervals of concavity. So I hope I answered your question. I'm trying to look here. Yeah, Jamie, you were right. It would be 2, not 2x. I got too many places to watch, to be honest with you. And so thank you for being patient. Okay, now I got some messages here. Could we 59, 60? Could we also do the 40? Thank you. The negative infinity. Okay. Other questions? What else would you like to take a look at? $39. All right. So let's go back here. 39. All right. So let's go to 38 so we get in the same vicinity. Yeah, won't really be able to get close. So let's just go over here. Okay, 39. Number 39. There it is. What do we have for directions? Find the points of inflection and discuss the concavity. So this is definitely second derivative because it's asking us for points of inflection. All right. So let's rewrite this and get ready to take the derivative. Okay. First derivative, product rule. The first times the derivative of the second. We chain rule, but it's 1 plus the second times the derivative of the first. Okay, let's rewrite this a little bit. So we've got x on the top, we've got a 2 on the bottom, and we have an x plus 5 to the 1/2 on the bottom. Over here, we have square root of x plus 5 on the top. Okay, so, before we do the second derivative, this is, I would get a common denominator. And so let's do that right now. So in other words, I would like to have the denominators be the same. So I'm going to multiply this top and bottom by what we need to get common denominator with that. Okay, and now when we bring this together, now we can bring the numerators together. We have a common denominator of 2 times the square root of x plus 5. And on the top, we have an x plus, and over here, what's going to happen is if you take the square root of x plus 5 times the square root of x plus 5, you get x plus 5 times 2, which is 2x plus 10. And then bring that top together, you get 3x plus 10 over 2 times the square root of x plus 5. Okay, now it's time to take second derivative. Let's rewrite. Equals 3x plus 10 times 1/2 times x plus 5 to the 1/2. Okay, so ready for the second derivative. Again, we can put the 1/2 out in front, right? Let me think. Yeah, I was going to think we can multiply that through too. Let's just leave it out in front. Now, let's multiply it out. Okay, so that would be 3/2 x plus 5. Okay, product rule. That's not the derivative, that's the function rewritten. So now I gotta, that's the first derivative now rewritten. All right. So now the first times the derivative of the second plus the second times the derivative of the first. Got all kinds of stray marks here. All right. So let's simplify. 3x plus 3/2 x plus 5 on the top. We got a 2 on the bottom, and we have a square root of x plus 5. And over here, we have a square root of x plus 5 and times 3/2. Okay. So the big question is, when is this equal to 0? Well, let's see. Let's get a common denominator again. So once again, I need to multiply top and bottom by, let me change back to black so we can try to keep from being mixed up here. I want this to have, so I'm going to multiply the top and bottom by the square root of x plus 5. That'll give us a common denominator. And on the top, we will have 3/2 x plus 5. Over here, we're going to have x plus 5 after we take it times itself, and 3 times that is 3x plus 15. Okay, so now the question is, when is this equal to 0? Only when the top is equal to 0. And so, let's just go to the top. So we'd have 0 equals 3/2 x plus 3x plus 20. So let's subtract 20 from both sides. Sorry. Penmanship sometimes a little bit rough with this thing. Okay. So what's 1.5? What's 1.5x plus 3x is 4.5x, which we could write this way. And then we could just multiply both sides by 2/9. Yeah, sorry. Let's try that again. Whoa. Sorry, I got lost. So where are we? There we are. So negative 20 times 2/9. So negative 49 evidently is a point of inflection. So now we could test it. So that's our break point. Now we could take a number to the left of that and test the second derivative at that. And our second, yeah. So I don't know. Let me just take a look at a plot of that. What was our function? Our function was x times the square root of x plus 5. X times the square root of x plus 5. X times the square root of x plus 5. Get rid of the blue. So there's our function. Okay, what did I find out? Where are we now? We're back here. So that supposedly is a point of inflection, negative 49ths. Let's just take a look now at the graph. Negative 49ths. Negative 49ths is approximately what? Um, 40 divided by 9. 4 and 4/9. Okay. Negative 4 and 4/9. So right about in there is our point of inflection. It doesn't look right. It does not look like a point of inflection. Yeah, I'm going to have to, I'll tell you what, I'm going to, afterwards, this is a long problem. I'm going to have to double check my work, and I will send everybody a corrected one. So 39, is that, what are we just working on? Yeah, so 39, I will redo, and I will send to everybody, okay? It doesn't look like that came out right, and I must have done an algebra error. I will double check that. Is there another question? Anybody else want to bring up an issue related to the test? So I'll follow up in just a little while here. I'll follow up with that number 39. So Claire, it's interesting. You were the one that asked me about when to apply the second derivative test. Well, 39 definitely is a place where you have to do that because it's asking you about concavity. So that one's a kind of a dead giveaway. You have no choice but to do it that way. And then set your second derivative equal to 0. That's that neutral point of inflection point, and then go on either side of the inflection point and just run a quick test of some representative value, and then you'll know concave up, concave down. Remember, it is possible on either side of a so-called second derivative equals 0, it is possible that on both sides it could be concave the same way. That's rare, but you could have concave down and then concave down, which means that that point of inflection wasn't a true point of inflection. Even though its second derivative was 0, it doesn't have to alternate between concave up and concave down, or concave down and concave up. Anyone else? Did you update the review assignment based off of what you have on the test? I don't know what that means. Did I update the review assignment based off of what you have on the test? You mean after I wrote the test, did I go back and update these priorities? I think is what you mean. I am no further on the test at this moment than I was the other day in class. I've got it, I don't know, maybe about half done. So no, there's nothing to update. I'd still say those priorities that we had, these priorities are still pretty much correct. I'm not going to get more exact than that. I think I answered your question. Let me know if I didn't. Okay, well, oh yeah. All right. Do I have another message? I don't. Okay, I think that's it. I'll see you tomorrow for the test. Thank you.